Hello, math magicians. Welcome back to the number jungle. So today we're going to be using Euler's method to figure out a very good approximation of this function here, 0.3 past 0, 2. Now otherwise we'd have to do a ton of anti-differentiation right here, but Euler's method makes it a little bit simpler. Not necessarily computationally, but definitely simpler in terms of calculations. It's just sort of number crunching. So what we want to start out with is setting up a quick and easy table, because if you don't do this, you can very easily get lost. So you want x, y, and dy dx. So we're starting out at 0, 2, and at 0, 2, we can see that x is going to be sine of 0, that is 0, so dy dx is also going to be 0. Now, when we add 0.1 for the next step, we're going to have 0.1, and then again it's going to be 2. And then we're going to look at this and we're going to see sine of 0.1 times sine of 2. Now, I'm not going to calculate that out because that's going to be uglier than sine of 0.1 sine of 2. So I'll just put that in here. And the next step is going to be plugging that slope and the next x and y values into the next part of the function. So for the second step, we're going to progress on to x equaling 0.2 and y equaling 2 plus sine of 0.1 sine of 2 all over 10. And the reason it's going to be all over 10 is because this is going to be the slope over a full change in x value, while we're only moving over 1/10 here. And we can now calculate the slope, and we'll find that the slope is sine of 0.2 times sine, and this is going to look ugly, but sine of 2 plus sine of 0.1 sine 2. And this is one place where it's very easy to mess up just by looking at this wrong, all over 10. So for the third and final step, and I'm going to draw the y out here just because it's going to be big, ugly, and not necessarily easy to work with. We're going to see 0.3 for the x value, because again we're just moving up by 1/10 each time. But so now we are going to be moving, when we move over 1/10, we're going to be moving up a slope of this whole thing right here all over 10. I don't expect that to look very nice, and that's fine. But so it's going to be this prior y value, 2 plus sine of 0.1 sine of 2 over 10, and then plus sine of 0.2 times sine. And as a matter of fact, this box itself is too small just because it is such a deeply oversized calculation, but sine of 0.2 times sine of 2 plus sine of 0.1 sine 2, and then all of this is going to be over 10. And then again, all of this right here is going to be over 10 as well. So at this point we can see that the final x value is going to be 0.3, not too shabby, comma, all this right here. Now, I'm going to write this in just once more so you can see it very comprehensively. That will be 2 plus sine of 0.1. Well, all this right here. You get the picture. So if we were to do this 10 times, it would end up being absolutely huge, and I don't even want to imagine how many sines and there would be and how much canceling out there would be possible. So that sort of thing is best left up to the computer, but I hope that this has been informative on how you can figure out a very accurate approximation of a function at a point using Euler's method rather than taking the time to differentiate this here and cancel everything out and create a function that way. So, thank you very much for listening, and I'm glad we made it out of the number jungle alive.